In the name of Allah, the most gracious, most merciful. Hello everyone. This is Dr. Tariq Masood. Thank you very much for watching my videos and your wonderful support to make this channel a grand success. We are a partner, a family. Please subscribe and share our channel if you haven't done so far. We as a team can work together to convert our challenges into opportunities and opportunity success stories. These success stories can be monetized into value addition. Thank you very much again. Okay, we are still discussing a smart grid control challenges model. So in earlier lecture we have given a brief about what is the smart grid and why we need a smart grid to be implemented. Okay, on my lecture number 3 we are still discussing a smart grid behavior and what are the challenges. Okay, smart grid operation and control challenges. So today I'm going to discuss my lecture number 3, introduction. We are still. So in my earlier lecture we have discussed in lecture number 1 why electricity is needed for our civilizations. We have also discussed power functionality. Then we discussed energy efficiency from generation to consumption. Then we have also discussed ultimate goal for a smart grid. So on my lecture number 2 we have discussed a power system infrastructure development plan. Then we have also discussed a power system complexity, power system limitations, and we have also given brief about reactive power significance and its management. So on my next slide, I will give you my brief about my 100 lecture plan on a smart grid, and then I will give you highlights for today's lecture. Okay, the understanding of the facts, concept and technology. So we have planned to deliver a 100 lecture on facts technology on smart grid basically. So we will start from fax technology concept, power semiconductor devices, voltage source converters, self and line commutative current source converters, SVC and STATCOM operations, static series compensators, static voltage phase angle regulators, combined compensator UPFC, special purpose fax controllers, and application will demonstrate a couple of application fax devices implemented in United States. What we are going to deliver after implementing fax technology, shaping the global energy delivery, facts on resolving gridlock, and delivering clean and pure power energy in the world by large. Takeaway points from lecture number 3. Okay, first we will discuss reactive power management, challenge to manage reactive power, balanced reactive power, challenge at AC power system. So these are the key takeaway points from my lecture number 3. Okay, I express my deep gratitude to all faculty members, student and leadership, in particular VCs and deans of the universities as listed here. UET Lahore, NFC Multan, RCT Gujranwala, Mehran, NED Habib, NAST International Research, Karachi Electric, Distinguished Lecture, IEEE Qatar sections, University of District Columbia, University of Texas Arlington, Texas Tech University, University of Bath, Qatar University, Texas A&M Qatar, University of Granada, University of Salamanca, COMSATS Abbottabad, City University Peshawar. Okay, as we have discussed lecture number 1 and 2, just we are going to give a highlight what we have discussed earlier. Basically, what are the key elements? Why we need a smart grid? Smart grid evolutionary development, fundamental approach for smart grid operation and challenges. So technically, what are the driving factors which we need to consider in order to deliver the required results? first boundary is called the grid condition and requirements. This is the first operating boundaries we need to understand and to determine its criticalities. So what are these criticalities? Variable power supply, integration of distributed resources, increase distance between resources and load. And number 2 is called the operational factors. What are the operational factors? That is operational factors or operational factors boundaries. Greater transmission network complexity, aging infrastructure, and lack of expert and high power delivery. Okay. Then number 3, external influences or external boundaries. That is what we need to do it. So what it demonstrates, first, a legal and regulatory framework, integration of renewable energy resources, CO2 reduction, and energy efficiency. In order to deliver the result or to operate your power system within their operating boundaries, what we need to do? A complex grid structure required, a smart solution. Okay. Now, just a recap, we have also discussed in my lecture number 1 and 2 as well. What is basically a demonstrate a fundamental characteristic of a smart grid? What are the smart grid fundamental characteristics? First is self-healing. What do you mean by self-healing? The grid rapidly detects, analyzes, responds, and restores. That is important to understand. That is first key elements or key deliverables from the smart grid, self-healing. Number 2, empower and incorporates the consumers. That is the second elements of the smart grid. Ability to incorporate consumer equipment and behavior in grid design and operation. Number 3, tolerant of attack. Very important. Number 3 as well. Grid mitigates and resilient to physical and cyber attack. Number 4, provide a power quality delivery. Needed by the 21st centuries, users are based on CMBA curves. Grid provides a quality power consistent with consumers and industry needs. Number 5, accommodate a wide variety of supply and demand. That is very important, that you have a different type of demand and supplies as well. Grid accommodates variety of resources including demand, response, combined heat and power, wind, photovoltaic, and use efficiency. So last year fully enabled and is supported by the competitive market. That is the last attempt from as far as the smart grid is concerned. So these are 6 deliverables must witness when we are going to implement a smart grid operation control challenges. This is continue from lecture number 3. First, how to manage reactive power in power system operation. First, overhead lines and cables behavior. Overhead power transmission lines are mainly absorb reactive power if the electric load is greater than the cell. Surge impedance loading. Number 1, we need to understand. So what is that? The overhead power transmission lines are mainly absorbing reactive power if the electric load is greater than the cell. Surge impedance loading. So certainly the load is all the time above than the cell. Okay, number 2. Overhead lines are producing reactive power if the electric power load is less than the cell, which happens rarely during a normal power system operation and control on the electric power grid. So normally it's happening very rarely, or you can say it never happened. Number 3 condition, in underground cable network is produced a large reactive power due to high charging current induced in the cables, thus loading them up below cell and making voltage control more challenging. That is important. So these are the 3 main factors which are absorbing and producing reactive power. Okay, in my next slide we will further discuss on reactive power management. Okay, reactive power management in transformer. Okay, if we can see from here, in the transformer observe reactive power in both sides. In shunt magnetizing reactance and leakage reactance, that is called the series reactance. As per analysis, the transformer can absorb 5% of its total rating when fully loaded. Number one. Number two, based on calculation, it can be observed that E is greater than V. This is my E source and this is my V voltage. V load side voltage and this is my source side voltage. So E is a greater than V and a sine angle. The variation between V and sine angle and E and sine angle gives the KVR, kilowatts amps reactance per phase absorbed by the leakage reactance, that is XL. So as I mentioned here, it can be witnessed that KVR value is equal to I square XL. This is also known as analogues of I square R, kW active power. These losses are due to series resistance of electric power lines. So if you can see here, this is my E source voltage, this is my load side voltage, and this is my IXL. So that is I square R kW active power. Okay, challenges to manage reactive power compensation in power system operation. Number one, large number of generating power plants supplying reactive power and vast numbers of loads in the system are not accurately modeled. That is first. Number two, reactive power requirement changes as loads vary, either from light load to peak load or their power factor changes. That is second challenge. Number three, high XOR ratio of transmission lines prevents a long distance transfer of the reactive power since much of it's buffered by I square X. So that is another biggest challenge. Number four, transfer of reactive power over long distance should be avoided and localized means of voltage control should be used if possible. So number fourth, the transfer of the reactive power over long distance should be avoided and localized means of voltage control should be used if possible. So what is the first challenge? Large number of generating plants supplying reactive power and vast numbers of the loads in system are not accurately modeled. Number one. Number two, reactive power requirements changes as load vary, either from the light loads to peak load as their power factor changes. Number three, high XOR ratio of the transmission lines prevents long distance transfer of the reactive power since much of the buffer by I square X. Number four, transfer of the reactive power over long distance should be avoided and a localized means of voltage control should be used if possible. Okay, what is the reactive power? So to make everybody to understand very easily, so this is my juice of glass which has two phases. One is a condensed phase of liquid and other is a foam phase. So the condensed phase of liquid is called the active power and the foam phase is called the reactive power. This is reactive power. Okay. So MVR sport is exchangeable with megawatt. The exchange rate could be up to 0.5 megawatt per MVR. So it means to deliver 0.5 megawatt, you need a 1 MVR in order to deliver a power systems, maintain seamless operation. In lecture number 2, we have discussed consequences, imbalance, compensation. If happen, what could be the impact on a power system operation? So on the first year, we are now going to discuss a balanced reactive power compensation as far as system voltage is concerned. If you can see here, light loading first. So what could be the consequences? Over voltage. It's capacitive or more. and inductive are less. So the system is compensated in the capacitor mode of operations. Number 2, cell loading. So consequences of flat load cell loading mean the capacitive and inductive are equal. Capacitive and inductive both are equal, balanced. So mean flat load, flat voltage. Number 3, heavy loading. Consequences under voltage. So mean more inductive and less capacitive. Okay. So we need to have a balanced reactive power in order to maintain a voltage level as required. So that's important, we need to understand. Okay, voltage and power angle stability issues. Okay, now we are going to discuss here transient stability and dynamic stability and voltage stability. First, what is the transient stability? Okay, transient stability are demonstrated in the graph a rotor angle versus a time span. This is my pre-fault condition, and this is a 0.1 second fault was created, and the system was isolated and it gone out of phase. That is transient instability. And second, if you can see here, the green light is also gone out of phase. That's dynamic instability. And after 3 seconds, the system was stabilized after implementing a solution. The curves, the waves was damped out. Okay. On the dynamic stability, same here, rotor angle and time span. Okay, this is my pre-fault condition here, and this is a t 0.0 second. The fault was created. So as fault was created, the red line show isolations was purely damped, and then light blue color dotted line show the oscillation was great and negatively damped out, and light blue the oscillation was damped reasonably. So the system was after 3 seconds. In voltage stability, if you see here, this is my line number 1 and line number 2. Here is my power source and this is my voltage. Okay. Now it is showing your voltage versus time again. If my line number 2 is stripped due to any reason, so the slight increase in the loading, and the voltage start decreasing, and after 15 seconds the voltage collapse. So this is how the 3 stability are impacting a power system operation. On my next slide, we are going to discuss thermal limit of AC power transmission system and why we need fax devices to implement these solutions. Okay, what are the challenges at AC power transmission system? Okay, as per the APRI analysis or database, so this is my voltage, this is my cell, and this is a typical thermal rating. 230 kV, 150 cell and 400 thermal rating. Similarly, 345, 400, 1200, 500, 900, 2600. Okay, if my line is operating at 500 kV line voltage and my cell will be 900 and thermal rating can go up to 2600. Okay, now if you can see here, the left hand side, my 3 arrows, the first arrow demonstrate here cell stability limit, and second red arrow demonstrate here the cell limit, and third green arrow show the typical thermal rating. Okay, and the blue arrow, small arrow, it demonstrate unused capacity. Okay, Now, the biggest challenge, how to utilize a maximum capacity of power transmission system. So remember, the uncontrolled power flow limit also causing many problems. First, it can cause low power transfer capability. Number 2, bottlenecks. Number 3, loop flows. In order to address these issues, we need to implement smart solutions, in particularly fax devices, to deliver the result as planned or as demand. Okay. Today we have discussed 4 topics. First, we discussed reactive power management. Then challenge to manage reactive power. What are the challenges? Balanced reactive power, and then we have discussed challenge at AC power transmission system. Thank you very much for your precious time to make everything possible. Next topic, this lecture is still continue. These are the my research paper already published. You can explore more. Thank you very much for your precious time. As a message here, together everyone achieve more. Please send me your feedback and comments t.masood.dr@bath.edu. Please stay at home, stay safe, inspired and blessed. Thank you very much for your precious time.